All right, my friend, let's work through this circle puzzle together very carefully, because there are several beautiful geometry ideas hidden inside it. And by the end of the problem, we're going to find the area of the entire circle. We are given a circle containing a horizontal segment of length 8, a vertical segment on the left of length 6, and a short vertical segment on the right of length 3. All the indicated corners are right angles. Our goal is to determine the area of the circle. Let's begin by labeling the important points. Let the left end point of the horizontal segment be point A, the right end point be point B, the top end point of the short vertical segment be point C, and the bottom end point of the left vertical segment be point D. Let O represent the center of the circle. Now let's extend the horizontal segment through point B until it reaches the circle at a new point E. Next, extend the vertical segment through B downward until it reaches the circle at another point, which we'll call F. Now, let's draw a horizontal segment from point D to meet the vertical line through B at point G, making a right angle. Notice something important here. The figure A, B, G, D has 4 right angles, so it forms a rectangle. Whenever we have a rectangle, opposite sides are equal. That means side AD equals side BG. We are given that AD equals 6. Therefore, BG must also equal 6. That's our first useful result. Now let's focus on the vertical chord CF. The upper segment BC is given as 3. By the symmetry created in this construction, the lower segment GF is also 3. Therefore, the entire segment BF equals BG plus GF. Substituting the values we have, BF equals 6 plus 3, which gives us 9. So now we know that the lower portion of the vertical chord has length 9. Next, we're going to use a very powerful theorem known as the intersecting chords theorem. This theorem tells us that when two chords intersect inside a circle, the product of the two segments of one chord equals the product of the two segments of the other chord. In our diagram, the horizontal chord AE and the vertical chord CF intersect at point B. Therefore, AB multiplied by BE equals BC multiplied by BF. Let's substitute the values we already know. AB is 8, BC is 3, and BF is 9. So we get 8 multiplied by BE equals 3 multiplied by 9. 3 multiplied by 9 is 27. Therefore, 8BE equals 27. To isolate BE, divide both sides by 8. This gives BE equals 27 divided by 8. Great. Now we can find the entire horizontal chord AE. Since AE consists of AB plus BE, we have AE equals 8 plus 27 divided by 8. Let's rewrite 8 as 64 divided by 8 so that the denominators match. Then AE equals 64 divided by 8 plus 27 divided by 8. Adding the numerators gives 91 divided by 8. So the length of chord AE is 91 divided by 8. Now let's connect point D to point E with a straight line. This new segment is going to be extremely important. Notice that angle DAE is a right angle. This is where we apply Thales' theorem. Thales' theorem says that if an angle inscribed in a circle is 90 degrees, then the side opposite that angle must be a diameter of the circle. Since angle DAE is 90 degrees, the segment DE must be the diameter of the circle. That is a huge breakthrough because once we know the diameter, finding the radius, and then the area becomes straightforward. Now let's focus on right triangle DAE. One leg is AD, which equals 6. The other leg is AE, which equals 91 divided by 8. The hypotenuse is DE, and since this is a right triangle, we can use the Pythagorean theorem. Remember, the Pythagorean theorem tells us that in a right triangle, the square of the hypotenuse equals the sum of the squares of the other two sides. So, DE squared equals AD squared plus AE squared. Substituting our values gives DE squared equals 6 squared plus the quantity 91 divided by 8 whole squared. 6 squared is 36. 91 squared is 8,281, and 8 squared is 64. Therefore, DE squared equals 36 plus 8,281 divided by 64. To combine these terms, let's write 36 with denominator 64. 36 equals 2,304 divided by 64. Now add the fractions. We get DE squared equals 2,304 divided by 64 plus 8,281 divided by 64. Adding the numerators gives 10,585 divided by 64. Therefore, DE squared equals 10,585 divided by 64. Taking the square root of both sides gives DE equals square root of 10,585 divided by 8. Remember, DE is the diameter. The radius is half of the diameter. Therefore, radius r equals DE divided by 2, which equals square root of 10,585 divided by 16. Now, we're ready for the final step. The area of a circle is given by the formula pi r squared. Let's substitute our radius. Area equals pi multiplied by the quantity square root of 10,585 divided by 16 whole squared. When we square a square root, the square root disappears, leaving 10,585 divided by 256. Therefore, the area equals 10,585 pi divided by 256. If we use pi approximately equal to 3.14159, we get an area of approximately 129.9 square units. And there we have it, my friend. The area of the circle is approximately 129.9 square units. What I really like about this problem is how it combines several important geometry concepts into one elegant solution. We used properties of a rectangle to find missing lengths, then the intersecting chords theorem to determine another segment, then Thales' theorem to identify the diameter, and finally, the Pythagorean theorem to calculate its exact length before finding the area of the circle. If you followed every step up to this point, you're building a very strong geometry foundation. If this explanation helped you understand the problem, don't forget to like the video, subscribe to the channel, and leave a comment telling me which theorem was your favorite in today's solution. I always enjoy reading your comments and seeing your different approaches, and I'll see you in the next mathematics lesson.